Welcome to today's video. What can you do with aerogel? This is a nice movie of a 3D printed graphene oxide aerogel microlattices. This material is very lightweight, highly conductive and compressible. You can see the layers printed layer by layer. This is another picture of 3D printed graphene oxide aerogel microlattices. And they have many applications, for example, in electronics, in energy storage, as catalysts and as filters. This is how aerogel looks like. It feels like styrofoam to the touch. It contains 90 to 99.9% air by volume. Aerogel is has a nanosized dendrite structure with air pockets, and this light color comes from Rayleigh scattering. Another very impressive picture of boron nitride BN aerogel of 1.8 cubic centimeter volume on human hair. You can see how lightweight this material is. Its mass density is just 0.6 milligrams per cubic centimeter. This is a nice picture of a dandelion of the seed head. The seed head works with the parachute principle. It is carried by the wind and falls to the ground. And if it's not eaten by an animal, it will grow to a new flower. Aerogel is so light that it can be placed on top of a dandelion without breaking it. Another very fascinating property of aerogel is its high surface area of up to 1,000 square meters per gram. This is another very impressive experiment. That's a 2.5 kilogram brick on 2 grams of aerogel. Here's the aerogel. In this case, it's silica aerogel. It is known to be very robust. Has made it several times into the Guinness Book of Records with its unique properties. This aerogel has a melting point of 1200 degrees Celsius and is hygroscopic, which means it loves water. Another impressive experiment, that's a flower on aerogel, which is heated by a Bunsen burner. This aerogel is known for its very low thermal conductivity. The nanopores give air very little room to move, and that inhibits both the conduction and convection, and that's how aerogel protects the flower from getting burnt. It's another type of aerogel, that's cellulose aerogel. Its lowest possible density is 0.5 milligrams per cubic centimeter. It's environmentally friendly and can be used for insulation. The flammability of this material can be reduced by treating the surface with chemicals, for example, with aluminum oxyhydroxide, AlOOH. This is how the aerogel synthesis works. That's the Sol gel process. First step is the hydrolysis and polymerization. You get Sol, which is a colloidal solution. Second step is the gelling. You get the wet gel. And the final step is the extraction of the solvent. This 3D structure is maintained, and that's how you can synthesize aerogel. And in this picture, you can see you can synthesize other materials, for example, dense ceramic, dense film, aerogel film, or ceramic fibers, or uniform particles. This is a picture of the final step of the synthesis of aerogel. That's the gel drying. With supercritical drying, you get aerogel with a 3D porous structure. With subcritical drying, you get zerogel. Zerogel has a destruction of the porous structure. That's the difference between zerogel and aerogel. This is another very interesting nanomaterial, that's nanogel. In this picture, you can see the many methods for making nanogel. For example, by desolvation or coacervation, or inverse emulsion, precipitation, electrostatic interactions, microtemplate polymerization, hydrophobic interactions, or by cross-linking mixers. Nanogel is a polymer cross-linked hydrogel on nanoscale. It is very interesting for medical applications because it is a delivery vehicle to cells. These are some examples of applications of aerogel. This is space-grade aerogel. It is a low-mass insulating material. Can be used for space travel, in the construction industry, filter technology, for cosmetics, and in the generation of solar thermal power. And these are more applications for aerogel. And use it for scattering filters for telescopes and as a target for the production of muonium. Muonium is an anti-muon that is orbited by an electron. Aerogel is also very interesting for catalysts. This is an artist's concept of the space robotic space probe Stardust. It was launched in 1999. Its mission is a collection of dust samples from the coma, comet Weil-2, and cosmic dust. This is the Stardust sample collection SSC. It is made of silica aerogel. After the sample collection, the SSC came back in a sample return capsule. And this was the result of this experiment. There was evidence for liquid water, for iron and copper sulfides, and the amino acid glycine was found. This is a close-up picture of the Stardust sample collector after landing in Utah. This is a close-up of the cometary impact here. This is another close-up. You can see two tracks of two comet particles that are stuck in aerogel. The aerogel is not broken. This is a picture from the pre-launch test of the aerogel material. And you can again see the material gets stuck, but there's no cracking. It makes aerogel a very interesting material for rockets because it is lightweight. However, the melting point is not high enough to use it for heat shields. This is a nice ashtray made of aerogel. You can again see the Rayleigh scattering, which gives this material its light color. And it's a very nice picture from the Penn State Center for Nanoscale Science from the Space Day 2004 with scientists. This scientists show aerogel and ferrofluids to kids. And since this is a picture from 2004, it may be possible that one of these kids is today a scientist. And that was a video about what can you do with aerogel, a fascinating material. You can check out the links in the description field. Thank you for watching. Have a nice day. Bye-bye.